Okay, for this problem we're going to prove that n squared plus 8 is always less than or equal to n cubed as long as n is greater than or equal to 3. Now this makes sense. The left-hand side is quadratic, it grows like n squared. The right side is cubic, and so it stands to reason that the right-hand side is going to grow faster than the left-hand side. So the right side ought to be bigger than the left-hand side as long as n is big enough. And big enough in our case is going to be base case of 3. So the proof of this one will be by induction on n. And this time the base case will be n equals 3 as opposed to the more common base cases of n equals 1 or sometimes n equals 0. Alright, n equals 3. Plug in 3, I get 3 squared plus 8 less than or equal to 3 to the third. Now is this true? 9 times 8 is 17. And this is 27. So, or 17 is less than or equal to 27, which is true. Okay, so that's easy. N equals k. Assume that k squared plus 8 is less than or equal to k cubed. Now we get to the k plus 1 step. Now, the left-hand side for this one will be k plus 1 squared plus 8. The target on the right will be k plus 1 cubed. And I'm not putting an equal sign here yet, or an equal sign here yet, because I have great flexibility with inequality problems. And this is the thing that makes inequality problems both easier and harder than the other types of induction problems. I can put either a less than sign or an equal sign or a less than or equal sign and I'll be okay. So that's a good thing. The bad thing is I have that kind of freedom, and so it's not necessarily always obvious how to end up with the target that I want. So let's kind of take this with the easy things I know. So equals, this is equal to k squared plus 2k plus 1 plus 8, that's what that's equal to. And in the other direction, if I were to multiply this out, that's equal to k cubed plus 3k squared plus 3k plus 1. So this is equal to that. And I need to somehow make these match in the middle. Okay, now by induction hypothesis, I know full well that k squared plus 8 is less than or equal to k cubed. So this top line is less than or equal to k cubed plus 2k plus 1 by induction hypothesis. And so I need to compare this to this. Well, here there's a 2k, there's a 3k. Now clearly if k is positive, 2k is less than 3k. So that's going to be less than k cubed plus 3k plus 1. If I add an extra k to this, if k is positive, then I've made it bigger. Also, if I added an extra 3k squared, I'll make it bigger again. So this is going to be less than this because k is greater than 0. So because k is greater than 0, this will be less than this, which in turn is less than this. Now, making those inequality steps is probably the hardest part of these kinds of induction proofs because you have tremendous flexibility in the types of lines that can go from one line to the next. But in any event, we've finally shown that the left-hand side is indeed less than or equal to the right-hand side, and so that is the end of the proof.